However, one volcano-tectonic earthquake was located at a depth of 5.5 kilometres below sea level, slightly west of the domes. That sentence was published on the 7th of August by a small observatory in the Caribbean, and almost nobody read it. The week before, the same observatory had written almost exactly the same sentence, about an earthquake nearly a kilometre shallower. Out of 230 earthquakes recorded beneath this mountain in 2 weeks, 228 came from the harmless place they always come from. 2 did not. Those 2 came from the corridor between the steam and the magma, and the second one came from further down. The mountain is Mount Pelée, and in 1902 it killed 29,000 people in under 2 minutes. So why is one earthquake a week now arriving from the one place nobody wants to hear from? But first, if you enjoy what we do here at Project Nightwatch, hit like and subscribe so you don't miss any of our nightly debriefs. And leave a comment telling me where you're tuning in from tonight. Now let's get into it. Part 1. The One That Didn't Belong. On the last day of July, a small office in a town called Saint-Pierre published a single page of numbers, and almost nobody read it. The office belongs to the Volcanological and Seismological Observatory of Martinique, and the numbers were routine. 124 earthquakes recorded beneath a mountain over 7 days, none of them strong enough to be felt by a single person on the island. None of them above magnitude 1, which is a magnitude so small that if you were standing directly on top of the epicenter, holding a cup of coffee, the coffee would not move. The vast majority of those earthquakes came from between 0.7 and 1.7 kilometres below the summit. That is somewhere between about half a mile and a little over a mile straight down. Shallow, weak, ordinary. This particular mountain has been producing earthquakes exactly like that, in roughly that place since the 1970s. And then, in the middle of that page, there is a sentence that changes shape the longer you look at it. However, one volcano-tectonic earthquake has been located at a depth of 4.6 kilometres below sea level, slightly west of the domes. 1 out of 124, roughly 3 times further down than everything else that week, and offset sideways from the summit, in a part of the mountain where the other earthquakes simply do not happen. That single line is the reason we are here tonight, because a week later, the same office published the same kind of page, with the same kind of numbers, and the same sentence appeared again. 109 earthquakes, almost all of them shallow, almost all of them too small to feel, and then, once more, the exception. However, one volcano-tectonic earthquake was located at a depth of 5.5 kilometres below sea level, slightly west of the domes. Same anomaly, same location, same singular, lonely, 1 out of 100 occurrence, and nearly a full kilometre deeper than the week before. That is the story, not the hundreds, the 2, and specifically the fact that the second one came from further down than the first, and there is a detail about that office that I have been saving, because it reframes everything about the tone of those bulletins. The observatory that publishes them is not in Paris. It is not in some regional capital at a comfortable remove. Its address is Morne-la-Rosette, on the Observatory Road, in Saint-Pierre, Martinique. Saint-Pierre is the town this volcano destroyed. The people writing these one-page reports, weighing every adjective, deciding whether to describe a displacement rate as slightly declining or simply declining, are doing that work inside the city limits of the place that got erased. When they write that the probability of eruptive activity in the short term remains low, they are writing it from the ground the pyroclastic flow crossed. That does not make them right. It does make them the least likely people on Earth to be casual about it. The mountain is Mount Pelée, Mount Pelée. It sits at the northern end of Martinique, a French island in the Lesser Antilles, roughly 1,500 miles southeast of Florida, and it is the most lethal volcano of the last century by a margin that is not close. On the 8th of May, 1902, it killed somewhere around 29,000 people, in less time than it takes to boil a kettle. We will get to that. We will get to all of it, because the details of what happened in 1902 are not decoration on this story. They are the reason a single line in a weekly bulletin is worth your attention at all. But before we go anywhere near 1902, I want you to understand precisely why one earthquake out of 124 is not a rounding error. Volcanoes are noisy, all of them. A volcano with a hot water system inside it will crack rock constantly, the way a house with pipes in the walls creaks at night. Those cracks register as earthquakes, and if you put enough instruments on a mountain, you will record hundreds of them, and the overwhelming majority will mean nothing at all. They are the sound of a system doing what it has always done. Scientists have a word for that: background. So when a bulletin says 124 earthquakes, your instinct is to fix on the number, because the number is large and the number went up. The week before, it was 45. The week before that, it had been higher. The counts bounce around like that, week to week, and they have been bouncing around like that for 7 years. Here is the uncomfortable thing. The count is the wrong number, because those 123 ordinary earthquakes were all happening in the same shallow layer, and that layer is not where the magma is. That layer is where the water is. Superheated water, pressurized steam, gas working its way through fractured rock about a kilometre under the summit. When that system swells, it cracks the rock around it, and you get exactly what we saw. A cluster of tiny, shallow, unfelt events. It is the volcanic equivalent of a kettle rattling on the stove. The one that came from 4.6 kilometres below sea level did not come from the kettle. It came from underneath it. And I need you to hold on to a specific piece of geography here, because everything in this story hangs off it. Beneath Mount Pelée, there are two systems, stacked. There is the hydrothermal system on top, the hot water and the steam and the gas, occupying the ground from just below the surface down to about 5 kilometres below sea level. And then, below that, there is the magma, the actual molten rock sitting in storage at somewhere between 5 and 8 kilometres below the summit, with a second, larger reservoir sitting deeper still. In between them, there is a boundary, a transition, and that transition is the single most important piece of real estate in this entire story, because everything that matters at a volcano happens when the top system and the bottom system stop being separate things. The earthquake at 4.6 kilometres happened in that transition. The earthquake at 5.5 kilometres happened just below it. Now. I want to be extremely careful with you here, because there is a version of this story that is dishonest, and it is the version that gets the most clicks. That version says a deadly volcano is waking up, an eruption is coming, and here is your countdown. That is not what the data says, and it is not what the scientists say, and I am not going to say it either. What the observatory says, word for word, in both of those bulletins is this: the probability of eruptive activity in the short term remains low. However, considering the observations accumulated over the past months and years, an evolution of the situation in the medium term, weeks to months, cannot be excluded. Read that twice, because there are two sentences in there, and they are doing very different jobs. The first one is reassurance, and it is genuine. The second one is not reassurance at all. The alert level on the mountain is yellow. It has been yellow since December of 2020, and it has not moved. There is no evacuation. There is no exclusion zone. Nobody on Martinique has felt a single one of these earthquakes. If you flew into the island tomorrow, you would find beaches, rum distilleries, a rainforest, and a mountain sitting quietly at the north end of it with clouds around the summit, exactly as it has looked for the better part of a century. And underneath all of that, once a week, for 2 weeks running, something has been making noise from the one place nobody wants to hear noise from. Here is what makes this genuinely strange rather than merely interesting. A year ago, the scientists who run that observatory published a research paper. It was not a press release, and it was not a warning. It was a careful, technical, 47-author study of everything the volcano had done since 2019, and in it, they laid out what they would be watching for. They named the signal. They said, in effect, this is the thing that would tell us the situation had changed, and the signal they named is connectivity. The moment when the shallow water system and the storage zone underneath stop being two separate compartments and become one connected pathway. They wrote that this connection is required before an eruption, and that it is often detected before eruptive activity begins. Then, this summer, an earthquake happened in exactly that zone, and then it happened again, deeper. That does not mean Mount Pelée is going to erupt. I want that on the record before we go one sentence further. It may mean nothing. Volcanoes produce anomalies constantly, and the overwhelming majority of anomalies resolve into nothing at all. This volcano has been in an unsettled state for 7 years, without so much as a puff of steam at the summit. But it does mean that the specific thing the specialists said they were watching for is the specific thing that just showed up, twice, in consecutive weeks, trending downward, and there is a second signal, running completely independently of the earthquakes, that I have not told you about yet. It started in May. It has nothing to do with seismometers, and when you put it next to the earthquakes, The two of them tell you flatly contradictory things about what is happening inside this mountain. One of them says the pressure is building. The other one says the pressure is easing. They cannot both be right, and right now, nobody on Earth knows which one is lying. Part 2, 230 earthquakes, and only 2 mattered. Let me give you the raw ledger, because the shape of it matters more than any individual line in it. Every Friday afternoon, the observatory in Saint-Pierre publishes a weekly report on Mount Pelée. It is 1 page, it has 2 sections, seismicity and deformation, and it ends with the alert level. It is written in French and released in English. It names the exact date and hour of the reporting window, and it carries a standing note that everything in it is preliminary and subject to change once the data has been properly reviewed. Here is what those pages have said this summer. For the week ending the 10th of July, 68 earthquakes of volcanic origin. 64 of them were volcano-tectonic, which is the technical term for an earthquake caused by rock breaking. 16 of those were above magnitude 0.5, and 4 were above magnitude 1, with the largest coming in at 1.51. They sat between 1.1 and 2 kilometres beneath the summit. The observatory attributed them, in its own words, to microfracturing within the volcanic edifice, linked to the overall reactivation of the volcano observed since 2019. That bulletin also contained 4 deep, long-period earthquakes, 3 of which they managed to locate sitting southeast of the mountain at depths between 17 and 22 kilometres. Hold that thought. We're going to come back to those in a serious way later, because they are a completely different animal from everything else on that page. The week before that one had produced 160 events. The 4-week rolling total, as of the 10th of July, was 396, averaging 99 per week. Then the numbers dropped. The week ending the 24th of July produced 45 earthquakes, less than half of the previous rate. If you were watching this mountain casually, that week would have looked like the story ending. Then came the week we started with. The 24th to the 31st of July, 124, 45 to 124. That is a factor of 2.76 in 7 days. Every single one of those 124 was volcano-tectonic. Not one exceeded magnitude 1. The vast majority came from between 0.7 and 1.7 kilometres below the summit. Nobody felt anything. The 4-week rolling total climbed to 331, averaging 84 to 85 a week. And then that one line. One event at 4.6 kilometres below sea level, slightly west of the domes. The following week, the 31st of July to the 7th of August, produced 109 events. And this is where the bulletin gets genuinely unusual, because for the first time this summer, the observatory had to break the total into 3 categories instead of 1. 106 volcano-tectonic earthquakes, none above magnitude 1, vast majority between 0.9 and 1.3 kilometres below the summit, plus the exception at 5.5 kilometres below sea level, slightly west of the domes. 2 low-energy shallow hybrid earthquakes at 1.2 kilometres below the summit, and 1 deep long-period earthquake located east of the mountain at 26 kilometres depth, magnitude 0.7. Nobody felt any of it. The rolling 4-week total rose to 372, averaging 93 a week. Now let us do something the headlines have not done, which is put those numbers against what normal looks like at this specific mountain. Before all of this started, the observatory had a baseline. Between January of 2015 and April of 2019, Mount Pelée produced 1,069 of these earthquakes across more than 4 years. That works out to 251 a year, 19 a month, 19 a month. The week ending the 31st of July produced 124. In 7 days, this mountain produced more than 6 months of what used to be normal for it. And it gets starker if you go back further. Between 1995 and 2013, across 18 years, the total was 584 earthquakes. The median was 10 a year. 10. In an average year in the 1990s, this volcano produced fewer earthquakes in 12 months than it now produces before breakfast on a busy Tuesday. So, yes, objectively, unambiguously, by the mountain's own historical standard, the current activity is elevated by a factor of roughly 20. And now the honest counterweight, because I am not going to sell you a number without its context, and this particular counterweight is enormous. This is not the peak. It is not close to the peak. It is not even in the same order of magnitude as the peak. In December of 2020, Mount Pelée produced 493 of these earthquakes in a single month, which the observatory's scientists described as a 25-fold increase over baseline. In April of 2021, it hit 614 in a month, and for a few years that stood as the record for this episode. And then came the autumn of 2025. I want to give you this figure from the most boring possible source, because that is what makes it credible. In November of 2025, a member of the French National Assembly submitted a written question to the government about how France was preparing for an eruption of Mount Pelée. The government answered in June of 2026, in writing, in the official record. Their answer states that activity peaked over the months of September and October 2025, when 4,750 earthquakes were recorded on average over that period, before declining again from November. 4,750 a month. Local reporting from the time carries the same picture. More than 4,000 tremors in September alone, against roughly 30 in a typical month. More than 2,200 in a single week. Normalise that so it lines up with the weekly figures we have been discussing. 4,750 a month works out to somewhere around 1,090 a week. The week ending the 31st of July 2026 produced 124, so the current activity, the activity generating headlines about a deadly volcano shaking again, is running at roughly 1/9 of what this mountain was doing 11 months ago. Read that again, because it is the single most important corrective in this entire story. Last autumn, Mount Pelée produced 9 times as many earthquakes per week as it is producing now. There were more than 2,000 in 1 week, and nothing happened. No eruption, no steam, no evacuation. The alert level did not move off yellow, and by November the numbers were falling again. Which means that if the count is your evidence peaked last year and has been collapsing ever since. Today's rate is high against the pre-Unrest baseline, and it has climbed sharply over the last 2 weeks. Both of those things are true, and it is a fraction of what this volcano did last autumn without consequence. So we are back to the same conclusion from a completely different direction. If you are watching the count, you are watching a number that was 9 times larger 11 months ago and told you nothing, and there is a better way to measure this than counting events, which is to measure the energy they release. Counting earthquakes treats a magnitude 2 the same as a magnitude 0.3, and those two things are not remotely comparable. Every full step up the magnitude scale is roughly 32 times more energy released. A magnitude 2 is not twice a magnitude 1. It is 32 of them, so the researchers did the arithmetic. Before all this began, in the 4 years from 2015 to 2019, the earthquakes they could accurately locate beneath Mount Pelée released about 26 megajoules a year. That is the reference level. It is, in absolute terms, a trivial amount of energy. 26 megajoules is roughly what a small car engine puts out in 10 minutes of ordinary driving. Then the Unrest arrived. 2019 came in at 36 megajoules, 38% above reference. 2020 came in at 273, which the authors described as a nearly 8-fold increase. 2021 came in at 252, still 10 times the reference level, and then it fell off a cliff. 2022, 27 megajoules, essentially back to baseline. 2023, 75, and the first half of 2024, just under 8 megajoules, which annualizes to below the pre-Unrest reference level entirely. Look at that shape. A spike in 2020 and 2021, a collapse in 2022, a partial rebound in 2023, and then, by the middle of 2024, a volcano that was releasing less seismic energy than it had been before any of this started. That is what a fading episode looks like. That is what the scientists were describing when they wrote their study, and it is why the paper reads the way it does. They were documenting something that appeared to be winding down. The largest single earthquake of that entire period, for reference, was a magnitude 2.0 on the 31st of January, 2023. It released 63 megajoules, which was 9.4% of all the located earthquake energy of the whole episode. One event, 9% of 5 years of energy. That is how skewed these distributions are, and it is another reason the raw count misleads you, and one more piece of honesty, which most coverage of this story has skipped entirely. The 4-week rolling totals this summer have gone 396, then 331, then 372. That is not a clean climb. That is a jagged line that went down and then came back up. If you drew it on a chart and squinted, You could tell yourself almost any story you wanted about it. Which is exactly why the count is the wrong number to be watching. Think about what the count is actually measuring. It is measuring how much rock is cracking in a shallow layer about a kilometre under the summit, and that layer is full of superheated water. When the pressure in that water system nudges up, more rock cracks, and the number goes up. When it nudges down, the number goes down. The count is a pressure gauge on the plumbing. It is a real measurement, and it tells you something real, and what it tells you is how the kettle is doing. It tells you nothing whatsoever about what is happening 3 and 4 and 5 kilometres further down. For that, you need a different kind of event. You need an earthquake that comes from somewhere the ordinary ones never reach. And in the 2 most recent weeks of published monitoring, out of 230 earthquakes recorded beneath Mount Pelée, exactly 2 came from down there. One at 4.6 kilometres below sea level, one at 5.5 kilometres below sea level, 0.8% and then 0.9% of each week's total. If you were building a case that this volcano is escalating, you would not build it out of the 228, you would build it out of the 2. So what exactly is down there, at 4 and 5 and 6 kilometres below sea level, that makes those 2 events worth more than everything else on the page combined? Part 3. The corridor. Cut the island in half and look at it from the side. At the top, the summit of Mount Pelée, about 1.4 kilometres above sea level, with 2 lava domes sitting in the crater. Those domes are the plugs left behind by the last 2 eruptions, the one in 1902 and the one that ran from 1929 to 1932. They are the scar tissue. Just under the surface and running down to roughly half a kilometre above sea level, you have the shallow hydrothermal system. Hot water, but not extraordinarily hot. Below 374 degrees Celsius, below 221 bar of pressure. This is the part of the system that feeds the thermal springs on the flanks, the ones with names like the Chaude River and the Clare River, where the water comes out warm enough to notice and not much more. Below that, from about 0.2 kilometres below sea level down to about 5 kilometres below sea level, is where things get genuinely strange. Because in that zone, the water is above 374 degrees Celsius and above 221 bar, and at those numbers water stops being water in any sense you would recognise. That is the critical point. Past it, you get a supercritical fluid. Not liquid, not steam, something with the density of a liquid and the behaviour of a gas, capable of moving through rock the way a gas moves and carrying dissolved minerals the way a liquid carries them. It is the most aggressive solvent in nature. It dissolves rock. It travels through fractures a normal liquid could never enter. And when it depressurizes, it expands with enormous violence. That supercritical zone, from about 0.2 down to about 5 kilometres below sea level, is the top half of our story. Now the bottom half. Somewhere between 5 and 8 kilometres beneath the summit, according to the chemistry of the rocks this volcano has erupted, sits the shallowest magma storage. Actual molten rock. Andesite, about 62% silica, stored at something like 875 to 900 degrees Celsius, with 5 to 6% water dissolved in the melt. Different methods put that reservoir at slightly different depths, some as deep as 12 kilometres, and the honest answer is that the exact number is not pinned down. Below that, deeper still, at somewhere between 12 and 16 kilometres, there is a second, larger storage zone. And beneath that, at 26 kilometres, is the moho, the boundary where the crust ends and the mantle begins. That number is going to matter enormously in a little while. So, water on top, magma at the bottom. 2 systems, stacked, separated by a few kilometres of rock, and in between them, at roughly 5 kilometres below sea level, there is a line that is not drawn on any map but governs everything. It is called the brittle ductile boundary, and it is the depth at which rock stops behaving like a solid and starts behaving like something closer to putty. Above that line, rock is cold enough, and the pressure is low enough that when you stress it, it snaps, it fractures, it breaks with a crack, and that crack is an earthquake. Below that line, the rock is hot enough and squeezed hard enough that when you stress it, it does not snap. It flows, slowly, over years, like glass in a very old window, and it does that without producing an earthquake at all. Which brings us to the thing that makes those 2 events remarkable. The scientists studying this volcano have placed that brittle ductile boundary at approximately 5 kilometres below sea level. The earthquake on the week ending the 31st of July was at 4.6 kilometres, just above the line. The earthquake on the week ending the 7th of August was at 5.5 kilometres, just below it. An earthquake below the brittle ductile boundary is not supposed to be easy. Down there, the rock is meant to bend rather than break. To get a snap out of it, you generally need something to change the equation, and the usual something is pressure from fluid. Push high-pressure fluid into a fracture, and you effectively unclamp the rock. You reduce the friction holding the two faces of a crack together, and rock that would otherwise deform quietly can suddenly slip with a jolt instead. So an earthquake at 5.5 kilometres below sea level, west of the summit domes, is not just a slightly deeper version of the ordinary ones. It is a different kind of event with a different implication. The shallow ones say the water system is pressurized. That one says something is pressurized in the transition zone between the water system and the magma, and that transition zone has a name in the scientific literature that I have been circling for the last several minutes. The researchers call it connectivity. Here is the argument, and I want to lay it out cleanly because it is the spine of everything else tonight. A volcano with magma sitting quietly in storage is not dangerous. Magma sits in storage under volcanoes all over the planet for thousands of years, at a stretch without doing anything at all. The Yellowstone caldera has magma under it right now. So does Naples. So does most of the Cascade Range. Storage is not the problem. The problem is a pathway. For a volcano to erupt, the magma has to get from where it is to where you are, and to do that it needs a route. A connected series of fractures running from the storage zone up through the intervening rock, through the water system, and out. Building that route is a physical process, it takes time, and it is not silent. Rock breaking is the loudest thing a volcano does before it does anything visible, which is why the scientists at this observatory wrote, in that paper I mentioned, that final connectivity through this depth zone is required for, and often detected prior to, the onset of eruptive activity. Required for, not associated with, not correlated with, required. If that is true, then earthquakes appearing in that depth zone are not just a curiosity. They are the observable form of the requirement being met. They are the sound of the route being built. And now put the two events back to back and look at the direction of travel. 4.6 kilometres, then 5.5 kilometres, in consecutive weeks, in the same place just west of the summit domes. The second one was deeper. Now I have to give you the other reading because there is one, and it is not weak. Fluid moves in both directions. A pathway is not a one-way street. High-pressure fluid working downward from an overpressurized water system into rock beneath it produces exactly the same kind of earthquake as magma working upward. From the seismogram alone, you cannot tell the difference between the two. A single event at 4.6 and a single event at 5.5 could be the shallow system leaking pressure downward into rock that has been slowly weakening for 7 years. That is not just a possible explanation. Given everything else this volcano has been doing, it may be the more likely one. And there is a third possibility, which is the least dramatic and the most probable of all. These preliminary depths were calculated automatically from a small network on a small island, and preliminary depths move when they are reviewed. The observatory says so on every bulletin, in writing. Those two numbers, 4.6 and 5.5, could both shift by hundreds of meters when the monthly analysis is done. They could turn out to be the same depth. They could turn out not to be in the transition zone at all. That third possibility deserves more respect than it usually gets, so let me explain where these depth numbers actually come from. To locate an earthquake, you need to see it from multiple directions. Each seismometer records the arrival of the fast compressional wave, and then, some fraction of a second later, the slower shear wave. The gap between those two arrivals tells you how far away the source was. Collect that distance from several stations, intersect the spheres, and you get a point in 3 dimensions. Horizontal position comes out of that process reasonably well. Depth does not. Depth is always the weakest number in an earthquake location because getting it right requires stations positioned above and around the source, and it requires you to know how fast waves travel through the specific rock in between, which varies enormously inside a volcano riddled with fractures and hot fluid and old lava. Now consider the geometry here. Martinique is a small island. The instrument network is dense by the standards of a volcano observatory, but it is still bounded by coastline, and the events we are discussing are around the size of a truck hitting a pothole. For an event that small at 5 kilometers depth, the uncertainty on that depth can easily run to several hundred meters. which means the difference between 4.6 and 5.5 kilometres, the entire basis for saying the second one was deeper, could in principle be measurement noise. And it means that the question of whether either of them was above or below the brittle ductile boundary at 5 kilometres is a genuinely open question rather than a settled one. This is exactly why the observatory publishes those bulletins with the standing note that the data are preliminary and subject to change depending on their subsequent analysis, and it is why they publish separate monthly bulletins with the reviewed locations. It is also, bluntly, why the scientists are saying they need several more weeks. They are not being coy. They are waiting for the numbers to stop being provisional, so we have 3 readings: magma establishing a pathway upward, water leaking pressure downward, or a rounding error in a preliminary catalogue. Any one of them could be right, and the honest position is that no one currently knows which. What is not in doubt is that the events happened, that they happened in consecutive weeks in the same location, and that the second was further down than the first, which would still be a fairly academic observation if it were the only thing this mountain had started doing this year. It is not. Since May, the summit of Mount Pelée has been physically moving. Part 4. The mountain is getting bigger. There is a line at the bottom of every one of those weekly bulletins that gets almost no coverage at all, and it is arguably more concrete than anything in the seismic section. Since May of 2026, the observatory has been recording ground displacements of several centimetres in the summit area of Mount Pelée. Not millimetres, centimetres. The top of the mountain has moved several centimetres since May, and it is still moving. Here is how they know. Scattered across the volcano and its flanks are 10 permanent satellite positioning stations. The same technology in your phone, but built to a completely different standard. Your phone is doing well to know where it is within a few metres. A permanent geodetic station, bolted to bedrock, logging continuously for years, corrected for the drift of the satellites, and the wobble of the atmosphere and the tide in the solid Earth itself can tell you where it is to within a couple of millimetres, which means that when a mountain swells, these things see it. Not by watching the summit rise, which would be almost impossible to measure directly. They see it because the stations move apart from one another, inflate something from the inside and the skin stretches, and the marks on the skin get further apart. That is what has been happening since May. And when the scientists model what shape of pressure source would produce exactly that pattern of stretching, the answer comes back consistent, week after week. An inflating pressure source at approximately 1 kilometre beneath the summit. 1 kilometre, which puts it right in the shallow water system, not in the magma. This is not molten rock pushing up under the crater. This is the top of the plumbing swelling, the same plumbing producing all those tiny shallow earthquakes, in the same place they are coming from. Now the number that matters, and the reason I have been building to this. In the 4 weeks ending the 31st of July, the maximum displacement rate was on the order of 1.2 centimetres per month. In the 4 weeks ending the 7th of August, it was on the order of 1 centimetre per month, roughly half an inch a month, and easing slightly. Half an inch does not sound like anything. It is the thickness of your finger. If a mountain grew half an inch and nobody had instruments on it, not one human being would ever know. So here is the comparison that gives it teeth. In that research paper the observatory published last year, covering 2019 through 2024, the scientists reported the deformation signal they had found. They called it a slight anomaly in the deformation of the volcanic edifice, beginning in mid-2021. They gave its size in exactly these words: a few millimetres in 1 year, a few millimetres in 1 year. And they thought that was worth reporting, worth modelling, worth arguing about in a peer-reviewed journal, because it was the first time anyone had ever measured a near-field shallow deformation signal at Mount Pelée. In the entire instrumental history of this volcano, the summit had never been caught moving before. When it finally happened, the movement was a few millimetres over 12 months, and they wrote that this first observation is significant and important in the context of the current unrest. That was the signal. A few millimetres a year. The signal running right now is 1 to 1.2 centimetres a month. Do the arithmetic and you land somewhere around 20 to 30 times larger on an annual basis from a source at the same depth, in the same place, just west or southwest of the summit. I want to be careful, because these are not necessarily identical measurements. Different reporting conventions, different processing, different time windows, and the weekly bulletin gives a maximum rate at a single station, while the paper described a modelled trend across a network. You cannot simply divide one by the other and call it a factor. But the order of magnitude gap is real, and it is not addressed anywhere in the weekly bulletins because the weekly bulletins are not written to draw that comparison. You only see it if you're holding the paper in one hand and the bulletin in the other. The volume involved, by the way, is small. When they modelled the 2021 signal, the pressurized source came out somewhere between 49,000 and 89,000 cubic meters, depending on which model you use. That is a body of fluid roughly the size of a large office building. It is nothing on the scale of a volcano. It would not fill a fraction of 1% of the magma storage underneath. But it does not have to be large to be meaningful. It has to be in the right place, and it has to be doing something new. There is also a second instrument on this mountain designed to catch exactly this kind of thing, and its results are worth knowing because they cut the other way. Buried in a borehole on the volcano are 6 tiltmeters, arranged at 3 different depths. A tiltmeter does one job. It measures whether the ground has tipped. If something inflates beneath you, the surface above it does not just rise, it domes, and the flanks of that dome tilt outward. A good borehole tiltmeter can detect a tilt of less than a millionth of a radian, which is roughly the angle you would get by lifting one end of a 10-kilometre plank by a centimetre. Through the whole of the Unrest from March of 2017 through October of 2022, those tiltmeters showed no clear trend. The researchers stated it plainly. The tilt data do not show any clear deformation of the Mount Pelée edifice associated with intrusion or the significant movement of magma at depth. And then, in a detail that is almost comically human, no tilt data were available at all for 2023 because the acquisition system broke. So one instrument saw a few millimeters and thought it mattered. Another instrument saw nothing at all. The scientists chose to report both, including the failure, which is what honest monitoring looks like from the inside. They also went and stood on the mountain repeatedly to check. Beyond the 10 permanent stations, there were temporary campaigns, 22 stations deployed across March and April of 2021 for more than 10 days each, 14 stations from late April to May of 2022, 22 more from September to December of 2022, another deployment in the autumn of 2023. That is an enormous amount of fieldwork for a signal of a few millimeters on steep tropical terrain, and it tells you how seriously they were taking a number that small. Their own caveat on the result is worth reading, because it is the opposite of overselling. The models are simple, they said, assuming the mountain is a uniform elastic solid, which it obviously is not. The displacements are very small, and the signal-to-noise ratio is quite low, especially in the vertical. All of that gives the observation an intrinsic uncertainty in terms of its interpretation. And then, having said all that, they still concluded that this first observation of a near-field shallow-depth deformation signal at Mount Pelée is significant and important in the context of the current unrest. That is the framework we are inside. A few millimeters a year was significant and important, and they were nervous enough about it to hedge it 4 different ways, and now the part that refuses to resolve cleanly. Over the 2 most recent bulletins, the displacement rate went down, 1.2, then 1. The observatory noted it both times with the same phrase, slightly declining in comparison to the previous month, slowing down, which is good news, which is in fact the single most reassuring number in this entire story, except that at the same time, over the same weeks, measured by different instruments in the same network, the earthquake count nearly tripled. The pressure is easing, the rock is breaking faster. Both of those statements are true, both were measured by the same observatory, and they are pointing in opposite directions. Part 5. 2 instruments, 2 answers. Anyone who has spent time around volcano monitoring will tell you the same thing, and it is not comforting. The instruments frequently disagree, and the disagreement is usually where the actual science lives. Let me set the 2 signals side by side one more time, cleanly. The seismometers say the shallow system is being stressed harder. 45 events, then 124, then 109. Rock cracking at 2 to 3 times the rate of a month ago, plus the reappearance of event types that had gone quiet, plus 1 anomaly a week from far below where the ordinary events live. The satellite positioning stations say the shallow system is being stressed less, 1.2 centimeters a month, then 1. A pressure source at a kilometre depth that is still inflating, but inflating more slowly than it was. There are only a few ways to reconcile that, and each one implies something different about what happens next. The first and most benign is that the pulse is ending. A finite amount of fluid moved into the shallow system in May. It pressurized the rock around it. The rock has now cracked enough to accommodate it, and the pressure is bleeding away. On this reading, the earthquakes are the pressure being released, not the pressure building, and the deceleration in the deformation is the direct consequence of that release. The system is finding its new equilibrium. In a few weeks, both numbers come down together, and this whole story ends as a footnote in a monthly bulletin. The second is that the source has stopped growing, but the rock is still catching up. Deformation measures how much the ground is moving right now. Seismicity measures rock failing under accumulated stress. Those are not the same clock. You can stop pushing on something and have it keep breaking for a while afterward, the way a bridge under load keeps ticking and popping long after the truck has parked. On this reading, the earthquakes are a lagging indicator of a push that has already happened, and again, this quiets down. The third reading is the one nobody wants, and nobody can rule out. The deformation slowed because the shallow system stopped taking new fluid, and it stopped taking new fluid because the fluid found somewhere else to go. If the top of a hydrothermal system is sealed, and something is feeding it from below, the pressure has to go somewhere. It can lift the ground, which is what we have been measuring. It can crack the rock, which is what the seismometers have been counting. Or the seal can start to fail, and the fluid can begin moving through, in which case the ground stops rising because the pressure now has an outlet. On that third reading, a falling inflation rate is not the system relaxing. It is the system opening. There is a fourth possibility I should name, and it is the least dramatic and quite possibly the most likely. Both numbers may simply be inside the range of ordinary week-to-week wobble at a volcano, and we may be doing what humans always do with two noisy time series, which is find a relationship in them because we are looking for one. That is a genuine risk in this kind of analysis, and I do not want to pretend otherwise. The earthquake count at Mount Pelée has bounced between 45 and 160 in the space of a few weeks this summer with no clear driver. The rolling 4-week totals went 396, then 331, then 372, which is not a trend, it is a wobble. The deformation rate went from 1.2 centimetres a month to 1 centimetre a month, and if you handed those two numbers to a statistician without telling them what they were, the statistician would ask, reasonably, whether the difference was larger than the measurement error. So when I say the two signals contradict each other, hold that lightly. It may be a contradiction. It may just be noise being read as narrative, which is a thing this entire genre does constantly, and which I would rather flag than commit. I cannot tell you which of those three is happening. Neither can anyone else, and I want to be extremely clear that the observatory's own reading leans toward the first two, because their stated probability of a short-term eruption remains low. That is their professional judgment, made with the full data set, and it deserves more weight than my speculation or yours. But I will point out that we have watched this exact contradiction play out twice in the last 3 weeks at two other volcanoes, and it did not resolve either time. 10 days ago we looked at Campi Flegrei, under the western suburbs of Naples, where the caldera produced its largest earthquake since instrumental records began, and where the uplift rate had been falling for months while the seismicity climbed. Same shape of paradox, rock breaking harder, ground rising slower. The interpretation there involved a system that had passed out of elastic behaviour into permanent unrecoverable deformation, which is a polite way of saying the rock had stopped springing back and started staying broken. Before that, on the 24th of July, we looked at Mount St. Helens, which produced a recharge swarm while the edifice was deflating rather than inflating. Magma arriving, ground sinking, contradictory, well documented and entirely normal for that volcano. 3 volcanoes in 3 weeks where the instruments told different stories about the same mountain. That is not a coincidence, and it is not a conspiracy. It is what monitoring actually looks like when you get close enough to see the individual measurements rather than the headline. And I want to press on the word sealed for a moment, because it is doing more work in this story than any other word in it. The researchers wrote that the top of the hydrothermal system at Mount Pelée may be variably sealed and was subjected to overpressure. That is not a metaphor. It describes a real physical process, and it is one of the more elegantly grim things in volcanology. Hot water carrying dissolved minerals rises through fractured rock. As it climbs, it cools and depressurizes, and the minerals it was carrying come out of solution and precipitate on the walls of the fractures it is travelling through. Silica does this beautifully. Over years, the fractures line themselves with mineral deposits, then narrow, then close. The system builds its own lid out of the material it was transporting. This is why an obviously seething, unstable volcano can present a completely quiet surface for decades. It is also why the surface being quiet proves absolutely nothing about what is underneath, which is worth remembering the next time you see a photograph of Mount Pelée with clouds around the summit and think, well, that looks fine. The other consequence of a lid is that pressure builds under it, and there are only 3 places for that pressure to go. It can push the ground up, it can crack the rock, or it can breach the seal. For 7 years, Mount Pelée has been doing the first 2, and that is exactly why a falling inflation rate is not automatically good news. If the ground has stopped rising because the source stopped pushing, that is the system relaxing. If the ground has stopped rising because the pressure found a new route, that is something else entirely, and from the outside on a graph the two look identical. Which is why the single anomalous earthquake matters so much more than either the count or the swelling. The count tells you about the water, the deformation tells you about the water. Both of them are describing the top kilometre of a system that has been noisy for 7 years and that has produced precisely nothing. The event at 5.5 kilometres below sea level is the only thing in either bulletin that is describing what is happening underneath the water. And to understand why that distinction is the whole ballgame, you have to know what these 7 years have actually looked like and how close this volcano came to being declared quiet again. Part 6. 7 years of nothing. The 1st of April, 2019, that is the date the observatory uses as the start line, and in April of 2019 the mountain produced 126 earthquakes in 2 main swarms, each lasting about a day at relatively shallow depths of up to 4 or 5 kilometres below the summit. To appreciate what that meant, you have to remember the baseline we established. 19 events a month. So April of 2019 produced roughly 6 months of normal in 30 days, in 2 bursts, and then it kept going. Nobody announced anything. There was no alert, no warning, no news coverage. There was a volcano that had been essentially quiet since its last eruption ended in 1932, whose summit fumaroles had gone out in 1970 and never come back, suddenly producing earthquake swarms. There was also something happening further out, away from the summit, that took a while to make sense of. Between December of 2018 and August of 2019, the network picked up 28 events at depths between 9 and 18 kilometres, well below the shallow swarms and well outside the summit area. And on the 25th of April, 2019, 3.5 weeks into the Unrest, there was an earthquake in the Dominica Channel 15 to 20 kilometres away, magnitude 3.8. Ordinarily, nobody would think twice about it, except that when the researchers worked out its mechanism, it came back weird. A normal tectonic earthquake is almost entirely what is called double couple, meaning 2 blocks of rock sliding past each other. This one was only 41% double couple. 31% of it was something else again, and 27.5% of it was volumetric, meaning part of that earthquake was rock changing volume rather than sliding. That is the signature you get when fluid is involved. So you have a fluid-flavoured earthquake, 15 kilometres from a volcano, in the exact month that volcanoes started producing swarms after decades of quiet. If you wanted to argue that something triggered the reactivation of Mount Pelée, that is where you would start, and people have. The researchers went and checked, because that is their job. Their conclusion was that it does not seem to be associated with a change in stresses significant enough to induce volcanic seismicity 15 to 20 kilometres away, and that no deformation consistent with a magmatic intrusion at depth was detected on the network following it. The stress, a magnitude 3.8, can transmit falls off brutally fast with distance, and the shallow swarms had already begun before it happened. Suggestive timing, insufficient physics. Through the rest of 2019, the seismicity increased systematically, month after month. By December, it was running at 297 events a month, and then, in November and December of 2019, something appeared on the satellite imagery that had nothing to do with earthquakes at all. On the southwestern flank, above the confluence of 2 rivers with the unremarkable names of the Upper Clare and the Chaude, a patch of forest started to die. Nobody noticed it at first. It showed up in a retrospective search of the archive once people knew to look. It was clearly visible by January of 2020, and it was formally identified in November of that year, and given a designation that tells you everything about how these things get handled institutionally. It was called VEG-1. On the 26th of December 2020, someone spotted it visually. 3 days later, a helicopter went up to confirm it. What they found was a zone of strongly degraded, leafless dead vegetation, with fractures in the ground running through the middle of it, 20 to 60 centimetres wide and 2 to 3 metres deep, traceable for tens of metres across the slope. And here is the part that I find genuinely unsettling, more than any earthquake statistic in this entire story. There was no fumarole, no steam, no visible gas escaping from any crack or orifice, no smell. When they flew over it with a thermal camera, there was no heat anomaly. When they went back through the satellite thermal archive, there was no heat anomaly there either. The forest had been killed by something invisible. In February of 2021, a ground team hiked in with instruments and found it. Carbon dioxide seeping diffusely and passively out of the soil at concentrations of up to 7,800 parts per million, against a normal background of about 400. Colourless, odourless, heavier than air so it pools in the soil and in low ground, and it displaces the oxygen the roots need. The trees suffocated from underneath, standing up over months, and from any distance at all the hillside looked completely normal until the leaves came off. More zones were found afterward. Veggie 2, 3, 4, 5, 6. Veg 6 only started developing in early 2024. Veg 2 crept south along the eastern rim of what is probably an old steam explosion crater. Meanwhile, the seismicity kept climbing. In November of 2020, for the first time, the instruments recorded hours-long harmonic tremor, a continuous humming signal with a fundamental frequency around 1.8 Hz. Tremor is a different beast from an earthquake. An earthquake is a crack. Tremor is sustained, and it is generally associated with fluid moving continuously through a constriction, the way a pipe sings when a valve is partly open. In December of 2020, the authorities raised the alert level to yellow, and that same month the count hit 493, which the scientists later described as a 25-fold increase over baseline. That was also the month a new type of event showed up for the first time, shallow hybrids. Remember that word. It is going to come back in a few minutes, and it is going to matter. April of 2021 hit 614 events in a month, and for several years that was the high water mark. That summer, the gas showed up somewhere new, and this one is genuinely strange. At the mouth of the Pelée River, on the Caribbean coast, in less than 11 metres of water, bubbles started coming up out of the seafloor. By February of 2022, the observatory had mapped the area of active submarine emission at 1,570 square metres. The bubbles were essentially pure carbon dioxide. There was a weak thermal anomaly with the water at most 2 degrees warmer than its surroundings, and the seawater above the site had gone slightly acidic, with a pH of 6.25 against the 8.12 measured there in September of 2021. Carbon dioxide dissolving into seawater makes carbonic acid. So the volcano was quietly acidifying a patch of the Caribbean off its own coastline, and the only reason anyone knows is that somebody reported bubbles. There were other reports too, of the kind that do not appear in any official dataset but that stay with you. Hikers and canyoners working the upper Pelée River, less than 200 metres from the original dead vegetation zone, have described the smell of hydrogen sulfide there for years, which is the rotten egg smell of volcanic gas. And in 2019 and 2020, canyoners reported that a fixed rope they had left in place for descents had been partly dissolved by acid, to the point where it broke into shreds. Something in that gorge was eating rope, and then, gradually, it started to fade. Through 2022 and 2023, the shallow activity dropped away. The energy release collapsed to near baseline in 2022. 2023 finished with 233 events for the whole year, which is, in the researchers' own phrasing, just barely below the yearly average baseline of 251. By the first half of 2024, the volcano was releasing less seismic energy than it had been before any of this started. In 7 years of this, exactly one earthquake was ever felt by a human being. On the 4th of November, 2021, a magnitude 0.8 was felt by an observatory field team standing at the Chaude River. That is it. That is the entire felt history of a 7-year volcanic crisis. One event, felt by the people whose job it was to be standing on the volcano. Everything else in this story has been invisible. The gas that killed the forest was invisible. The swelling of the summit was invisible without satellites. The earthquakes were invisible without seismometers. Veg 1, the original dead zone, has since grown its vegetation back, and nobody can currently get to the site to find out whether that is because the gas stopped or because the plants adapted. A volcano that has been in crisis for 7 years, and there is nothing to see. So by the middle of 2024, if you had been following this, you would have concluded it was over. Peaked in 2021, faded through 2022 and 2023, back to baseline energy by 2024. An episode. A thing that happened. That is exactly the point at which 47 scientists sat down to write up what they had seen, and what they wrote is the reason a single line in a weekly bulletin 2 summers later is worth taking seriously. But before we get to their paper, there is one more thing that happened after they finished writing it, and it is the piece that most coverage of this story has left out entirely. In the autumn of 2025, Mount Pelée did something it had never done in the entire instrumental history of the observatory. In September of 2025, more than 4,000 earthquakes. In 1 week of that month, more than 2,200. The government's own figure for the September and October peak is an average of 4,750 a month, against a historic baseline of about 30 a month. That is not 25 times baseline. That is more than 150 times baseline, and it was 7 times larger than the April 2021 peak that the research paper had called the maximum of the episode. The observatory's director at the time, Jérôme Verne, was asked about it directly by local media, and what he said matters more than the number. Some of the events, he noted, had reached magnitude 2, which is around the threshold where a hiker on the summit might actually feel one. The swarm, he said, exceeded anything in the observatory's catalogue across roughly the 15 years the network has had its current capability. And then he listed what was not happening. No significant ground deformation, no surface phenomena, no new fumaroles, no degraded vegetation appearing, no change in the chemistry of the gas or the water, no change in the temperature of the springs, thousands of earthquakes a month, the largest swarm ever recorded at that volcano, and every other instrument on the mountain flat. By November, the count was falling. Through the winter and spring it kept falling, and the whole thing ended the way these things almost always end, which is with nothing. Now put 2026 against that. The earthquake count today is roughly 1/9 of what it was last September. On that measure alone, this year is a quiet year. But in May, the summit started swelling, which is precisely the thing the observatory's director said was absent during the biggest swarm in its history. And in the last 2 weeks, 1 earthquake a week has been arriving from the corridor between the water and the magma. Last autumn was the loudest this volcano has ever been, and it was accompanied by nothing. This summer is far quieter, and it is accompanied by 2 signals that were missing last time. Part 7. The paper that named the signal. It was published on the 2nd of July 2025 in Scientific Reports, under the title Ongoing Multiparameter Unrest at the Mount Pelée volcano on Martinique from 2019 to 2024. 47 authors, lead author F.R. Fontaine of the Institute of Earth Physics of Paris. It is open access, which means anyone reading this could pull it up right now for free and read every word of it. That fact alone dismantles a large amount of what is going to be said about this story online over the next few weeks. The most alarming statements anyone can make about Mount Pelée are not being hidden. They were written by the people who run the monitoring network, submitted to peer review, and published where anyone can find them. What they built was a synthesis. Seismicity, ground deformation, gas chemistry, satellite imagery, thermal springs and helium isotopes, all laid over the same 5-year window to answer one question. What is actually driving this? Their answer runs like this. A limited volume of magma, moving without producing earthquakes, entered the crustal storage zones somewhere between 6 and 16 kilometres down. It did not erupt. It did not reach the surface. It sat there, and it did what magma does, which is give off heat and give off gas. That heat and that gas, particularly carbon dioxide sourced from the mantle, rose into the hydrothermal system above it, and that system, crucially, was sealed. The top of it had healed over. Pressurize a sealed container and you get exactly what Mount Pelée produced. The ground lifts a few millimeters. The rock around it cracks in thousands of tiny events. Carbon dioxide finds whatever weakness it can and seeps out through the soil kilometers away, killing a patch of forest without producing a single wisp of steam. The abstract puts it in one sentence. This protracted unrest most likely reflects the ascent of a limited volume of magmatic fluids that reinvigorated the shallow hydrothermal circulation. It is worth pinning down what they mean by the storage zones, because the numbers are less precise than you would hope, and the imprecision is itself informative. There are two ways to work out how far down magma was sitting before it erupted, and both of them are forensic. The first reads the crystals. Minerals growing inside a magma body record the pressure and temperature they grew at, in their chemistry and in their structure, and if you can read those, you can convert pressure into depth. That approach puts the shallowest storage under Mount Pelée at 5 to 8 kilometres below the summit. The second approach takes the erupted rock into a laboratory, remelts it, and finds the pressure and temperature at which the observed crystals would be in equilibrium with the observed melt. That approach puts it deeper, 7 to 12 kilometres. There is a third line of evidence, and it is the absence of one. The volume of rock between roughly 6 and 9 kilometres below sea level under the summit is characterised by remarkably few earthquakes, a hole in the seismicity. And a hole in the seismicity is exactly what you would expect from a body of partially molten rock, because molten rock does not fracture, it cannot make an earthquake, it absorbs them. So the quiet zone and the crystal chemistry and the laboratory work all point at roughly the same band, and the researchers settled on a general statement: crustal magmatic storage zones located between 6 and 16 kilometres depth, with a deeper reservoir feeding a shallower one. Which means the corridor we care about, the one those two anomalous earthquakes came from, is the roughly 3 or 4 kilometres of rock sitting between the bottom of the supercritical water and the top of the shallowest magma. Not a large distance. On a road, it would take you 4 minutes. They have the chemistry to back it. The carbon isotope signature of the gas coming out of the ground and out of the springs is magmatic. Not biological, not from dissolving limestone. It came from molten rock. The helium isotope ratios sit in the range you get from mantle-derived gas, not from the crust. Something down there was outgassing, and its breath was reaching the surface. They also tracked how that breath changed over time. Helium and carbon dioxide concentrations rose from 2021 through the middle of 2022, and in the hottest of the thermal springs the helium enrichment went from 302% of saturation in September of 2021 to 1080% by August of 2022. Then it declined through 2023 and 2024. Their description of that shape is careful and clinical, a degassing pulse followed by near-state conditions. A pulse. Something arrived, exhaled, and settled. And here is the observation that should have gotten more attention than it did. Across the whole episode, the thermal springs never got hotter. The temperature readings at the Chaude River have not exceeded 36.8 degrees Celsius, the maximum measured back in March of 2009. Historically, this volcano has done that. Spring temperatures climbed from 53 degrees in 1960 to 83 degrees in 1967, and then fell away again over the following decades. So the volcano has a track record of heating its springs, and during 7 years of unrest, it has not done it once. That is a real, measured, unambiguously reassuring fact, and it is still true today. Now. The pattern in the seismic data is where this gets genuinely eerie, and it is the reason I keep coming back to that one earthquake a week. The researchers noticed that the seismicity did not just rise and fall, it migrated. Their phrase is a pattern of seismicity that deepened from top to bottom through time. Shallow earthquakes in 2019, right up near the surface. Tremor in 2020. Tremor plus shallow hybrid events in 2021. And then in 2022 and 2023, as the shallow activity collapsed, the deep events arrived. Deep hybrids and long-period events at 18 to 37 kilometres, straddling the boundary between the crust and the mantle. The noisy shallow part quieted down, and the quiet deep part started talking. Their reading of that is that the whole process progressively linked the surface to the storage zones, and then they wrote the sentence that this entire story turns on. Over the period of unrest, they said, this top-to-bottom mechanism has enhanced the connectivity of the surface to the areas of crustal magma storage, and they added why that needs to be carefully monitored, because final connectivity through this depth zone is required for, and often detected prior to, the onset of eruptive activity. They then named the two things that would need to be watched for. 1. A chemical destabilization of the magma storage zones due to magma ascent from depth. 2. Enhanced connectivity between the surface and the magma storage zones. That is a list of what to look for, published a year ago, by the observatory that would be doing the looking. And then they wrote down the timescale, and this is the number I would ask you to remember above all the others tonight. Given that the timescales from magma reservoir destabilization to eruption can be typically short, on the order of a few weeks to 1 or 2 years, they said, this is paramount to improve the assessment of the likelihood of new magmatic unrest. A few weeks to 1 or 2 years. That is not a prediction. Nothing in that sentence says anything is destabilizing at Mount Pelée. It is a general statement about how these processes run at volcanoes of this type, and it is the reason the observatory keeps writing that phrase in every bulletin. An evolution of the situation in the medium term, weeks to months, cannot be excluded. They are not being vague, they are quoting the physics, and to their enormous credit, the authors refuse to tell anybody how the story ends. Their words, it is impossible to determine whether the current decrease in the intensity of the unrest will eventually lead to a return to baseline activity for an extended period of time, or whether the unrest could resume and eventually evolve into more critical conditions at the volcano. They also included a warning about their own data that almost nobody quotes, drawing on other researchers' work. Shallow earthquake activity may not reflect the initial formation of a conduit, or the beginning of chemical instability in a magma storage zone. Those processes can happen without earthquakes at all, at depth, or long before seismicity escalates just prior to an eruption. Sit with that for a second, because it inverts everything. The loud signal is not necessarily the meaningful one, and the meaningful one can be completely silent. Which brings us back to a bulletin published on the 7th of August 2026, in which the shallow noise stayed loud, and 2 things showed up that had not been in the previous week's report at all. Part 8. The hybrids came back. 2 low-energy, shallow hybrid-type earthquakes located at a depth of 1.2 kilometres below the volcano's summit. That is the entire entry. 2 events, both feeble, both in the same shallow band as everything else. In a bulletin containing 109 earthquakes, that line looks like a footnote. It is not a footnote, and to explain why I have to tell you how volcanologists actually read a seismogram, because the amount of information in the shape of a squiggle is much larger than most people assume. When rock breaks, the crack radiates energy across a wide range of frequencies, and the high frequencies dominate. On a seismogram it looks sharp, a sudden onset, a spiky burst, and a quick decay. You can also clearly separate the 2 wave types, the fast compressional wave that arrives first, and the slower shear wave behind it. At Mount Pelée, these events sit between 5 and 30 Hz, and they are called volcano-tectonic. Every one of the 106 ordinary events in that bulletin was one of these, rock breaking. Now take a different situation. Instead of rock snapping, you have a crack already filled with pressurized fluid, and a pulse of pressure travels through it. The walls of the crack flex and resonate, the way a pipe organ resonates when air moves through it. That does not produce a sharp spike. It produces a long, smooth, low-frequency signal, 0.5 Hz to 5 Hz, with a slow onset and a long tail, and critically, no shear wave at all because fluids cannot transmit shear. These are called long-period events, fluid moving. Then there is a third category that is exactly what the name implies, a hybrid. It starts like a rock fracture, with the sharp, high-frequency onset above 5 Hz, and then it decays into the long, low-frequency resonance of a fluid-filled crack, which is to say, something broke, and then fluid rushed into the space where it broke and rang. That is a hybrid event. It is the seismic signature of a crack opening and immediately being invaded. At many volcanoes worldwide, an escalating hybrid earthquake count is one of the more reliable short-term precursors that exists, because it is the direct signal of fluid forcing its way through rock in real time rather than sitting in a reservoir. And the reason volcanologists trust that signal is worth spelling out, because it comes from a place uncomfortably close to Martinique. 250 miles up the same island arc sits Montserrat, and on Montserrat sits the Soufrière Hills volcano, which began erupting in 1995 and buried the island's capital city of Plymouth under ash and pyroclastic flows. That eruption has been monitored more intensively, for longer, than almost any other dome-building eruption in history, and one of the things that came out of it was a much better understanding of what escalating swarms of hybrid earthquakes actually mean when a dome is being pressurized from below. They mean magma is being forced through rock, not sitting, moving. And at Soufrière Hills they were repeatedly associated with the periods when the dome was growing hardest and when collapses and explosions followed. That is the same island arc, the same tectonic setting, the same style of andesitic dome-building volcanism, and the same kind of volcano that produced the flows at Saint-Pierre. It is the closest thing to a live laboratory for Mount Pelée that exists on Earth, and it has been running for 30 years. So when the observatory logs a hybrid event at Mount Pelée, it is logging a signal type whose meaning at a volcano exactly like this one has been studied to death by people 2 islands away. Now here is the history of hybrids at this particular volcano from that 5-year study. Across the entire episode from 2019 to 2024, the network recorded 54 hybrid events. 33 of them could be located well enough to trust, and they split into 2 clean populations, 25 shallow ones at less than 5 kilometres below the surface, 20 of those 25 within 2 kilometres of the summit, and 8 deep ones at 20 to 35 kilometres, 54 events in 5 years. The shallow ones first appeared in December of 2020. That is the same month the count hit 493 and the alert level went to yellow. They arrived at the height of that crisis and they clustered through its noisiest period. And they have returned whenever this volcano has gotten busy since. During the enormous swarm of late 2025, one weekly bulletin in November logged 16 shallow hybrid events alongside 218 ordinary ones. So hybrids are not exotic at Mount Pelée, and their presence by itself is not a red flag. What they are is a marker. They track the periods when fluid is actively forcing its way into fresh cracks in the shallow system, and they go quiet when it is not. On the 7th of August 2026, 2 of them appeared at 1.2 kilometres below the summit, in the same week that produced the anomalous event at 5.5 kilometres below sea level. They had not been in the bulletin the week before, and there is a detail buried in the energy accounting that reframes how much these events matter relative to their number. 54 hybrid events, out of many thousands of earthquakes across 5 years, is a fraction of a percent of the catalogue. But when the researchers added up the energy, the hybrids that could be located carried around 174 megajoules, which worked out to about 40% of the energy released by all the volcano-tectonic earthquakes combined. Read that again. A vanishingly small number of events, carrying nearly half as much energy as everything else put together, and 2/3 of that hybrid energy came from the deep ones, the 8 events between 20 and 35 kilometres, 8 earthquakes, roughly 115 megajoules, more than 4 years of the volcano's entire pre-unrest seismic energy budget, delivered by 8 events at the bottom of the crust. This is the pattern that runs through the whole dataset, and it is the reason I keep hammering on the same point. At Mount Pelée, the loud events are small, and the small events are loud. The hundreds of shallow cracks you can count on a bulletin are, energetically, almost nothing. The rare events from far below are where the actual work is being done. 2 hybrid earthquakes are not an emergency. The observatory did not describe them as one, and the alert level did not move. They were explicitly noted as low energy. On any reasonable reading, 2 small hybrids inside 109 events is a minor detail. But it is the return of a signal type that tracks fluid on the move, in a week when the count was elevated, in a week when something also happened 5.5 kilometres down, in a week when a third signal appeared that we have not even discussed yet. And that pattern, all by itself, is starting to look uncomfortably like a compressed replay of the one the researchers described unfolding over 5 years. Shallow rock fracturing, then hybrids, then something from far below. Except in 2019 through 2023, that sequence took 4 years to run. In the last fortnight of published monitoring, it has run in 2 weeks, and the last piece of it, the piece from far below, did not come from 5 kilometres, or 10, or 15. It came from the base of the crust. Part 9. 26 kilometres down. One deep, long-period earthquake located east of Mount Pelée at a depth of 26 kilometres, with a magnitude of 0.7. Magnitude 0.7. That is not an earthquake in any sense a person would recognise. It is a sound. If you could somehow stand next to it, 26 kilometres underground, you would hear something like a distant door closing in an empty building. The energy involved would not lift a bag of groceries, and it came from the base of the crust of the Earth. Let me put 26 kilometres into some kind of proportion. Commercial aircraft cruise at about 11 kilometres up. This event was more than twice that distance below sea level. The deepest hole humans have ever drilled, the Kola super-deep borehole in Russia, took 20 years of work to reach just over 12 kilometres, and it stopped because the rock at the bottom was hotter and more plastic than anyone had planned for. This earthquake happened at more than twice the depth of the deepest hole we have ever managed to dig, and the specific number matters enormously. Beneath Martinique, the boundary between the Earth's crust and the mantle beneath it, the Mohorovicic discontinuity, the Moho, sits at an estimated depth of about 26 kilometres. The event was located at 26 kilometres, at the Moho, at the floor of the crust, at the place where the material feeding this entire volcanic system comes in from below. Now, the word deep in the phrase deep long-period earthquake is not decoration, and neither is long period. Remember the taxonomy. Long period means the signal has no sharp high-frequency onset and no shear wave. It is low, smooth, resonant. It is not rock-breaking. It cannot be rock-breaking, because at 26 kilometres depth, and the temperatures that go with it, the rock down there does not break in the way surface rock breaks. It flows. So what makes an earthquake at the base of the crust? Fluid. Specifically, gas and melt moving through cracks and pockets under pressure, causing them to resonate. Deep long-period earthquakes are one of the more direct observations we have of magmatic fluid on the move at depth, and the observatory itself says exactly that in plain language in its bulletins. Their phrasing, deep long-period earthquakes, are characterized by signals containing only low frequencies and are associated with the movement of magmatic fluids deep within the Mount Pelée volcanic system. Associated with the movement of magmatic fluids. That is the observatory's own words in a public bulletin describing this class of event. Here is how rare they are at this volcano. In the 5 years covered by that study, the network detected 17 long-period events. 17. 9 of them were located reliably enough to trust, and in the researchers' words, they are all deep events located at around 20 kilometres depth, except for one located at 37 kilometres. 17 events in 5 years, and one showed up in a single week this month. To understand why anything is happening at the base of the crust under a Caribbean island at all, you have to know what Martinique is standing on. The Lesser Antilles are an arc, and an arc is what you get where one tectonic plate is being forced underneath another. Out to the east, in the Atlantic, the floor of the ocean is bending downward and sliding beneath the Caribbean plate at a few centimetres a year. Martinique, Dominica, Guadeloupe, Saint Vincent, Montserrat, the whole curved chain of them, sit on the overriding side, and they exist because of what happens to the slab going down. Ocean floor is wet, not just the sediment on top of it, but the rock itself, which has spent millions of years reacting with seawater and locking water into its mineral structure. As that slab descends, it heats up and it is squeezed, and at a certain depth, the minerals holding the water break down and release it. That water rises into the hot mantle rock above the slab, and here is the counterintuitive bit that makes volcanic arcs exist at all. Adding water to hot rock lowers its melting point, not by a little, by hundreds of degrees. Mantle rock that was solid becomes partially molten simply because water arrived. Geologists call it flux melting, and it is the same principle as throwing salt on an icy road. That melt is buoyant, so it rises. It collects at the base of the crust, at the Moho, where the density contrast slows it down. It pools there, it evolves chemically, and eventually some of it works its way up into the crustal storage zones we talked about, at 6 to 16 kilometres. So the base of the crust beneath Mount Pelée is not an inert floor. It is the loading dock. It is the place where new material arrives from the mantle and stages before going anywhere else. It is where deep magmatic gas separates out and starts looking for a way up. That is what a long-period earthquake at 26 kilometres is reporting on. There is more. Almost all of the ones in the study happened in 2022 and 2023, peaking in July of 2023, and that is precisely the window when the shallow activity had collapsed. When the top of the volcano went quiet, the bottom of it started talking. That inversion is the top-to-bottom deepening the researchers described, and it is the reason they concluded that connectivity was being established between the surface and the storage zones. Together, the deep hybrids and the long-period events in that study spanned 18 to 37 kilometres, sitting, in their description, just above or below the Moho at about 26 kilometres, and now stack the week ending the 7th of August into one picture. 106 ordinary rock-fracturing earthquakes in the shallow water system, All trivial, none felt. 2 hybrid events at 1.2 kilometres, the signature of fluid invading fresh cracks, returning after a long absence. 1 rock-fracturing earthquake at 5.5 kilometres below sea level, in the corridor between the water and the magma, 1 kilometre deeper than the same anomaly the week before, and 1 long-period event at 26 kilometres, at the base of the crust, of the exact type the observatory associates with magmatic fluids in motion. 4 separate depths, 4 separate signal types, 1 week. You could draw that on a diagram and it would look like a cross-section of the entire volcanic system, reporting in simultaneously, from the mantle boundary to a kilometre under the summit. I have to give you the counter-argument, and it is the same one as before, only stronger here. A single long-period event proves nothing. 9 of them were located across 5 previous years, in 1s and 2s, and none of those led anywhere. Deep events at arc volcanoes are a normal part of how these systems breathe. Subduction zone volcanoes are fed continuously from below, and the deep plumbing produces occasional low-frequency events forever, in the same way an old building settles. The observatory has not changed its assessment, and its assessment is that the short-term probability of eruption remains low. But there is a difference between a fact being unremarkable and a fact being uninformative. 1 event a week from the corridor, 1 event from the base of the crust, hybrids returning, count elevated, ground swelling since May. Any one of those, on its own, is a Tuesday at a volcano. All of them at once, at this volcano, is why an observatory that has spent 7 years telling people not to worry is now saying, in writing, that it needs several more weeks of observation before it can say what is happening. And to understand why several weeks of observation is a phrase that should make the hair stand up on the back of your neck rather than reassure you, you need to know what happened here on the 8th of May, 1902. Part 10, 2 minutes. Saint-Pierre was the finest city in the Caribbean, and everyone in the Caribbean knew it. 26,000 people, sometimes as many as 30,000, depending on the shipping. A theatre modelled on the one in Bordeaux, a botanical garden, stone buildings with red tile roofs stacked up the slope from a harbour full of masts, cobbled streets, a cathedral, a tram, electric light, a newspaper. It handled the rum and sugar trade for the entire island, and it was called, by people who had seen both, the Paris of the Caribbean. It sat about 6 kilometres from the summit of Mount Pelée, on the coast, at the bottom of a slope. The volcano had been misbehaving for months. There had been steam at the summit from the summer of 1900 onward. On the 23rd of April, 1902, the first freatic explosion happened, a steam-driven blast throwing out old rock and ash. Through the last days of April, the ash fell on the town thick enough that people swept it off their steps like snow. Sulphur fumes made animals sick. Snakes came down off the mountain into the outskirts. A wave of insects arrived. The river ran hot and then flooded, and on the 5th of May, a mud flow came down the Rivière Blanche and destroyed a rum distillery at the edge of town, killing everyone in it. There was an election scheduled for the 11th of May. A scientific commission was appointed, examined the situation, and concluded that Saint-Pierre was not in danger, that the mountain presented no more risk to the town than Vesuvius did to Naples. The governor came to Saint-Pierre with his wife to demonstrate confidence. People from the surrounding villages, frightened by the ash, came into the city because the city was where you went when you were frightened. The population went up. On the morning of the 8th of May, 1902, at 2 minutes past 8, the side of the mountain opened. What came out was not lava. Almost nobody dies from lava. What came out was a cloud, and the term the world learned for it in the aftermath was nuée ardente, glowing cloud, and it is one of the more elegant names ever attached to one of the worst things that can happen to a human being. Physically, it was a suspension of superheated gas, ash and rock fragments, so dense with particles that it behaved as a fluid rather than a cloud. And because it was denser than the air around it, it did not rise, it fell. It came down the southwest flank, hugging the ground, filling the valleys, following the terrain the way water follows terrain. Temperature, up to 500 degrees Celsius. Speed, over 200 kilometres an hour. 500 degrees is not a fire you feel approaching. It is well past the ignition point of wood, cloth, and hair, and it is roughly the temperature at which a domestic oven self-cleans. 200 kilometres an hour means that from the moment it left the mountain, it covered the 6 kilometres to Saint-Pierre in under 2 minutes, Under 2 minutes, not enough time to run. For most of the town, not enough time to stand up. It arrived at 8:02 in the morning, when the streets were full because it was a Thursday and people were going to work. The city was destroyed in that pass, not damaged. Stone buildings had their walls pushed over in the direction of the flow. 3-metre-thick masonry survived. Almost nothing else did. The heat set fire to everything combustible simultaneously, and the rum stores in the warehouses ignited and burned for days afterward. In the harbour, the ships at anchor were rolled over and set alight. One vessel, the Rodham, managed to get out with terrible casualties and made it to St. Lucia to bring the first word of what had happened. The Roraima burned at anchor with most of the people aboard. It is worth understanding why the cloud went down instead of up, because that single behaviour is what made it lethal, and it is not intuitive. When a volcano erupts explosively, the material blasted out is a mixture of gas and shattered rock, and whether that mixture rises or falls depends entirely on its density relative to the air. If it entrains enough air on the way up, the air heats, expands, and the whole column becomes buoyant, and you get the classic mushroom-shaped eruption column climbing into the stratosphere. That is the version of a volcano everyone has in their head, and it kills relatively few people directly. But if the mixture is too dense, or if it is directed sideways rather than upward, or if a column starts to rise and then loses its buoyancy and collapses back down, the whole mass becomes heavier than the atmosphere, and it does what any heavy fluid does. It flows downhill, and it accelerates. That is a pyroclastic density current, and it is not a cloud in any useful sense. It is closer to an avalanche made of gas and hot sand. It hugs terrain. It follows valleys and pours over ridges. Its leading edge can carry a surge of hot ash that spreads beyond the main body of the flow, which is why the fatality zone at Saint-Pierre extended past the visible deposit, and it moves too fast to outrun. 200 kilometres an hour is faster than a car on a highway, on terrain with no roads, in a mixture with no breathable air in it. Estimates of the dead run from 28,000 to 30,000. The figure most often used in the modern scientific literature is 29,000. 29,000 people, in under 2 minutes, in a city that had been told the previous week that it was safe. It remains the deadliest volcanic eruption of the 20th century, and nothing in that century came close. What happened afterward is worth knowing too, because it explains the shape of the mountain you see in photographs today. The eruption did not stop on the 8th of May. It ran for years. Flows came down the same valley repeatedly, and on the 30th of August 1902, another one killed a further 1 to 2,000 people in villages to the east that had been considered safe. Saint-Pierre itself, by then, had nobody left in it to kill. And out of the crater, slowly, something extraordinary grew. Magma too stiff and too gas-poor to flow was pushed upward through the vent as a solid mass, and it emerged as a spire. A tower of rock rising out of the summit, growing at times more than 10 metres a day. It was photographed obsessively. At its greatest, it stood roughly 300 metres above the crater floor, taller than most buildings on Earth at the time, a needle of solid lava standing on top of a mountain that had just erased a city. It was named the Spine of Pelée, and it crumbled as fast as it grew. Within a year it was gone, collapsed into rubble under its own weight. The domes those eruptions left behind are still up there. They are the domes the bulletins are talking about every single week, when they say the anomalous earthquake was located slightly west of the domes. That phrase in the bulletin, the one we have been circling all night, refers to the plug of 1902. The town, for its part, came back, not as it was. Saint-Pierre today has roughly 4,000 people, a fraction of what it held, and it is a quiet place with ruins folded into it. You can walk through the shell of the theatre. The observatory is up the hill, and the reason it matters tonight is not sentiment. It is that everything volcanology knows about this particular kind of death, it learned here. Before Saint-Pierre, the field did not have a proper concept of a ground-hugging pyroclastic density current. Afterward, it had a name for it, a type example, and a permanent understanding that the lethal product of a volcano is very often not the lava, not the ash column, and not the earthquake. It is a fast, hot, heavy cloud that runs downhill. At Mount Pelée, that kind of flow can travel about 10 kilometres, and the entire population of Martinique lives within 30 kilometres of an active volcano. There were survivors in the city, depending on how you count, either 2 or 3 out of a population of tens of thousands. And the pattern in who lived is the single most instructive thing in the whole event. Part 11. The three who lived. The most famous of them was in a prison cell, and he was in it because he had gotten into a fight. Ludger Silberis, born the 1st of June, 1874, sometimes recorded in the sources as Louis-Auguste Cyperis, was a labourer and sailor with a local reputation for trouble. On the 2nd of May, 1902, 6 days before the eruption, he was arrested after stabbing a man in a brawl. The details vary by source, which is what you would expect from a records office that subsequently ceased to exist. He was put in solitary confinement, and the cell they used for solitary in Saint-Pierre was a squat stone structure, half buried in the ground, with thick masonry walls, no windows, and a single narrow slit in the heavy door, facing away from the mountain and toward the sea. That description is not a colourful detail. That description is the entire reason he lived. Every element of it did a specific job, half buried, so most of its surface was insulated by earth. Thick stone, so the heat took a long time to conduct through. No windows, so the flow could not enter and fill the space. A narrow slit facing away from the volcano, so the pressure wave and the incandescent material had almost no aperture to get through. On the morning of the 8th of May he was inside it when the light changed. His account, given many times afterward, describes it happening almost instantly. The cell went dark. Hot air and fine ash came through the door slit. He was severely burned on his back, arms and legs. There was no air worth breathing, and he covered his mouth and held on. Outside, in a radius of several kilometres, essentially everyone was already dead. He was found days later still alive by rescue workers who heard him. He was pardoned. He recovered more or less, though he carried the burn scars for the rest of his life, and he was eventually hired by the Barnum and Bailey Circus and toured as, in their phrasing, the man who lived through doomsday. He died around 1929. The second survivor is less famous, and his account is in some ways more useful. Léon Compère-Léandre was a shoemaker who lived at the very edge of the city, on the outskirts, at the margin of the flow. He wrote down what happened, and what he described was sitting on his doorstep when he felt a terrible wind, then the ground shaking, then the sky going dark. He described people around him dying immediately, and he described his own legs burning, and he described getting up and running out of the city while everything behind him was on fire. He lived because he was at the edge, not because of anything he did. There is a third name that appears in almost every popular retelling, a young girl usually given as Havivra da Ifrile, who is said to have escaped into a sea cave or taken a small boat out into the harbour and been found drifting afterward. I want to be honest with you about this one. It circulates widely, and it is thinly supported in the scholarly record. It may have happened. It may be a story that attached itself to the disaster the way stories do, treated as something people say rather than something documented. Beyond the city itself, a few tens of people caught at the outer margins of the cloud survived, most of them badly burned. Now look at that list and pull out the pattern, because the pattern is the physics. One man lived because he was surrounded by rock. One man lived because he was at the outer edge of the flow. The others who lived were at the margins. That is it. That is the complete set of survival strategies available on the 8th of May, 1902, and neither of them was a decision. Notice what is not on the list. Being indoors did not save you, because ordinary buildings did not stop it, and in many cases collapsed on top of the people sheltering in them. Being upstairs did not save you. Being in the harbour did not save you. The ships burned. Being on the far side of the town did not save you, because 6 kilometres of city is nothing to a flow moving at 200 kilometres an hour. Being warned did not save you, because the warnings that existed had been officially contradicted. Only geometry saved people. Rock between you and the mountain, or distance beyond the edge of the cloud. And that is the thing that separates this hazard from almost every other natural hazard we cover. With a hurricane, preparation works. With a flood, elevation works. With an earthquake, building codes work, and they work spectacularly well. With a pyroclastic density current, there is no engineering solution available to a civilian population, and no shelter-in-place strategy that functions. The only intervention that has ever worked, anywhere, is not being there. Which is why the entire apparatus around Mount Pelée today, the seismometers, the satellite stations, the gas sensors, the weekly bulletins, the alert levels, the evacuation plans, exists for one purpose. Not to stop the mountain. Nothing stops the mountain. It exists to buy time to leave, and we know that works, because this same volcano proved it. When Mount Pelée erupted again, from 1929 to 1932 in the same style, with the same kind of flows down the same slopes, the authorities evacuated in advance. The eruption happened. The flows came down. The death toll was nothing like 1902. Same mountain, same mechanism, different outcome. The variable was warning and what people did with it. It is worth sitting with why the warning failed the first time, because it did not fail for lack of information. Everybody in Saint-Pierre knew the mountain was doing something. Ash had been falling for 2 weeks. A distillery had already been destroyed with everyone in it. Animals were dying. The river had run hot. People were frightened enough to be talking about leaving, and some did. What stopped the rest was not ignorance. It was authority, applied in the wrong direction, at the wrong moment, for reasons that had nothing to do with volcanoes. There was an election coming. There was a commission that examined the mountain and pronounced the town safe. There was a governor who came in person and stayed, which is the most powerful reassurance a public official can offer, and it killed him along with everyone else. And the villagers who came into Saint-Pierre in those final days did so for a reason that was completely rational on every day except that one. The city was where the institutions were. The city was where you went when things were going wrong. That is not a story about primitive people in 1902. That is a story about how human systems handle a hazard whose signals are ambiguous, whose timing is unknown, and whose worst case is expensive to act on. Which is precisely the situation that exists on that island right now, at Yellow, with an observatory saying the short-term probability is low and the medium-term cannot be excluded. Nobody is being lied to. The bulletins are published weekly in 2 languages. The alarming research is open access. The alert level is public. The difference between 1902 and today is not that the information is better hidden. It is that it is vastly more available, more quantitative, and delivered by an institution with a century of institutional memory about exactly this failure. Whether that is enough depends entirely on what the mountain does next, and on whether anybody is still paying attention by the time it does it. Which brings us to the uncomfortable question underneath this whole story. In 1889, 13 years before the city burned, this volcano gave its first sign that something had changed, and that sign looks a great deal like something the satellites picked up in 2019. Part 12, 1889. This paragraph is not in a tabloid. It is in the introduction to the peer-reviewed paper we have been discussing all night, written by the scientists who run the observatory as a piece of historical background. I am going to give it to you close to verbatim, because the wording is theirs and not mine. As early as 1889, the first signs of renewed activity of Mount Pelée were noted, with the appearance of a fumarole from a hole in the summit crater of Étang Sec, and damaged vegetation in the vicinity, a new opening at the summit, a steam vent, and vegetation dying around it. That is 1889, 13 years before the 8th of May. Now hold that next to 2019, new gas emission on the flank, and vegetation dying around it, over a patch of forest above the confluence of the Claire and the Chaude, detected on satellite imagery in November and December of that year. Different gas, technically. Different location on the mountain, technically. 1889 was a fumarole, visible, steaming, at the summit crater. 2019 was cold, invisible, odourless carbon dioxide seeping through soil on the southwest flank with no vent at all. But the observable, the thing a person standing there would actually see, is the same in both cases. Trees dying around a place where gas is coming out of a mountain that has been quiet. And it gets stranger. The 1889 hole disappeared. By 1899, the researchers write, rich vegetation was observed growing in its place. 10 years after the vent opened and killed the plants around it, the vent had closed, the ground had healed over, and the forest had come back. Now recall what has happened to VEG1, the original dead zone from 2019. In the paper published last year, the authors report plainly that the VEG1 zone has now revegetated, and they are candid that they do not know why. They have not been able to get back into that remote terrain. It might be that the carbon dioxide flux genuinely dropped. It might be that opportunistic plants moved in that tolerate more soil gas than the original forest did. Nobody knows. So run the 2 sequences side by side. 1889, event and dead vegetation. 1899, the vent gone, the vegetation back. The 4th of June, 1900. Fumaroles at the summit intensify and continue intensifying. The 23rd of April 1902, the first phreatic explosion. The 8th of May 1902, 15 days later, the city. Now, the modern one. 2019, gas from the ground and dead vegetation. By 2025, the dead zone revegetated, the episode apparently fading, the energy release below where it started. 2026 from May, the summit begins to swell. 2026, late July and early August. The count triples, hybrids return, and one earthquake a week begins arriving from the corridor between the water and the magma, getting deeper. 13 years, the first time. 7 years so far this time. Now I am going to do the thing that separates this from every breathless version of this story you're going to see, and tell you why that parallel is much weaker than it feels. It is a rhyme, not a schedule. Almost every volcano that has ever erupted showed unrest beforehand, so if you go looking for a precursor sequence in the record of an eruption, you will find one, every single time. What that tells you nothing about is the far larger number of volcanoes that showed exactly the same unrest, and then went back to sleep for centuries. The 1889 sequence looks meaningful because we know how it ended. If Mount Pelée had done all of that and then gone quiet until today, nobody would have written it down at all. Second, the two situations are not the same physically. 1889 was a summit fumarole. Fumaroles mean a connected pathway from a heat source to the surface, already open, already venting. Mount Pelée has had no fumaroles at all since 1970. What it has instead is diffuse, cold soil degassing on a flank, no visible vent, no steam, and no thermal anomaly detectable from a helicopter or a satellite. That is a much weaker surface expression than 1889 had, and the thermal springs, which historically climbed to 83 degrees in the 1960s, have not exceeded 36.8 degrees since 2009. Third, and most importantly, the statistics are against it. Over the last 25,000 years, Mount Pelée has produced 2 to 3 magmatic eruptions per 1,000 years. That gives you an average repose interval somewhere in the range of 330 to 500 years. The last magmatic eruption ended in 1932. That is 94 years ago. 94 years, against an average interval of 3 to 5 centuries. This volcano is not overdue. It is not close to overdue. If anything, it is early, and anyone telling you that Mount Pelée is due is either not looking at the numbers or is hoping you will not. There is also a scale question hiding inside that recurrence figure that changes how you should read it. Not every eruption at this volcano is a 1902. The record over the last 25,000 years alternates between two very different modes. There are the dome-building eruptions where stiff magma piles up at the summit and collapses periodically, sending flows down the flanks. 1902 was one of those, and so was 1929 to 1932. And then there are the Plinian eruptions, which are a different order of event entirely. Those are the sustained explosive columns, tens of kilometres high, that blanket the region in pumice and ash. Mount Pelée has produced them repeatedly, and 3 of the more recent ones can be dated around 79 of the Common Era, around 280, and around 1300. So the mountain runs both programs, which means that a statistic about how often it erupts is averaging together 2 hazards that would demand completely different responses, and neither of them is the thing currently happening, which is nothing. So why bring 1889 up at all? Because of what it tells you about tempo, not about timing. The 1902 sequence did not go from quiet to catastrophe. It went from quiet to a small ambiguous sign, to a decade of apparently nothing, to slow escalation, to a phreatic explosion, to the worst volcanic disaster of the century in 15 days. Volcanic unrest is not a ramp. It is a staircase with long flat sections and short vertical ones, and the flat sections are extremely convincing while you're standing on them. 10 years of nothing after 1889 was not a false alarm. It was the staircase, which is exactly the trap the observatory's own researchers warned about in that paper, in the most quietly alarming sentence in the whole document. The processes that lead to an eruption, they noted, can begin without earthquakes at all, deep down, or long before seismicity escalates just before an eruption. The quiet is not evidence of safety. It is just quiet. And this is why the phrase in the current bulletins deserves to be read carefully rather than skimmed. An evolution of the situation in the medium term, weeks to months, cannot be excluded. Put that next to the timescale from the research paper, that the interval from a magma reservoir being destabilized to an eruption is typically a few weeks to 1 or 2 years, and you can see what they are actually saying. They are not predicting anything. They are telling you how much runway the physics allows, and it is not much. Which raises the only question that actually affects anybody living on that island. If the mountain did escalate from where it is now, what would actually happen? Part 13. The Plan. There is a plan. It is called the Orsec Vulcan Plan. It is a French departmental civil protection framework, and it is triggered by the prefecture rather than by the observatory. That distinction matters. The scientists measure, the state decides. The plan is built around 4 levels of scenario, and its central mechanism is elegant on paper. 12 communes in the north of Martinique, the ones inside the hazard zone, are each paired with a reception commune in the south. A town in the north knows in advance which town in the south it is going to. Rivière-Pilote, with about 11,600 residents, is one of the designated receiving towns. At the other end of the scale, Grand Rivière, right at the northern tip of the island in the shadow of the volcano, has around 530 people. The alert level within that framework was raised to yellow in December of 2020. Yellow means vigilance. It means the scientific monitoring is intensified and the administrative machinery is aware, and it means very little else in terms of what a resident is asked to do. It has been yellow ever since, through the 614 events a month in April of 2021, through the collapse of activity in 2022, through the 4,750 a month in the autumn of 2025, the largest swarm ever recorded at this volcano, through the current escalation, 5.5 years at the same level, through everything. There is a fair criticism to be made of that, and I want to make it properly rather than cheaply. If a level never changes, what information does it carry? The reasonable answer is that these levels are tied to defined scenario thresholds and, more importantly, to actions. Moving up a level is not a mood. It commits an administration to doing specific things, and the things at the next level up involve moving tens of thousands of people, which has its own costs and its own risks and is not free to do wrongly. The observatory's own probability language has not changed either, which suggests the specialists believe the system is still in the same regime it has been in for years, but there is a genuine, documented weakness, and it did not come from a critic. It came from a drill. On the 31st of January 2026, an evacuation exercise was carried out, and the conclusion drawn from it was that in the event of an eruption of Mount Pelée, evacuation by sea would probably be the better option. By sea, not by road. The reason is arithmetic. Martinique is a small island with roughly 256,000 registered vehicles on it, and the road network in the north is exactly what you would expect on steep volcanic terrain. Narrow, winding, with very few routes and no redundancy. If you tell 12 communes to leave at once, everybody gets in a car and everybody arrives at the same 2 or 3 roads simultaneously. Anyone who has ever sat in a hurricane evacuation on a coastal highway understands the failure mode. A road network is a system with a throughput limit, and beyond that limit it does not degrade gracefully. It locks, and a locked road inside a pyroclastic flow hazard zone is not a delay. It is a body count with a timestamp on it. That is what the exercise found, and the fact that it was published is a point in the system's favour rather than against it. The people running that drill went looking for the failure and reported it, and the finding did not stay inside the drill. It has been argued about publicly on the island, in Martinican media, by people saying openly that it is time to properly test the volcano plan rather than assume it works. The question of how France anticipates an eruption of Mount Pelée has also been put in writing to the National Assembly in Paris as a formal parliamentary question. This is a live administrative argument, being had in public right now by people who live there. There is one more number that puts the whole preparedness problem in proportion, and it is the one that makes Martinique unusual among volcanic islands. The researchers describe Martinique as being among the most vulnerable regions in the world to volcanic hazards, and the reason they give is not the volcano. It is the geography. The island is small, and because it is small, the proportion of the entire population living 30 kilometres or less from an active volcano is essentially all of them. 30 kilometres, on an island you can drive the length of in about 90 minutes, with one volcano at the top of it and roughly 350,000 people spread below. That is not a place where you evacuate away from the hazard. There is no away. There is only south, and the south is where everyone else already lives. So the honest state of preparedness on Martinique is this. There is a real plan, with real pairings and real designated destinations. There is a monitoring network good enough to detect a magnitude 0.7 event 26 kilometres underground. There is an observatory publishing weekly, in public, in 2 languages, and there is a known bottleneck in the physical execution, which somebody has measured and written down, which is better than most places manage, and it is still entirely dependent on one variable: how much notice the mountain gives. There is one other consequence worth naming, because it is the one that will put this story on international news if it ever escalates, and it is not the one that matters most. Martinique sits under busy air corridors linking the Caribbean to North America and Europe. Volcanic ash and jet engines are catastrophically incompatible. Ash melts in the combustion chamber and resolidifies on the turbine blades, and aircraft have lost all engines flying through plumes that look like ordinary cloud. A significant explosive eruption at Mount Pelée would close airspace across a wide area of the eastern Caribbean and disrupt transatlantic routing for as long as the plume persisted. That is real. It would affect hundreds of thousands of travellers, and it is probably the reason most people in North America would hear the name Mount Pelée for the first time. But keep the proportions straight. The air travel disruption is the consequence that travels. It is not the consequence that matters. The consequence that matters is measured in kilometres on a slope in northern Martinique, and it takes under 2 minutes to arrive. And whether any of that ever becomes relevant comes back to a single, absurdly small question, which will be answered in a 1-page document, probably on a Friday afternoon. Part 14. What the Next Bulletin Says. Let me strip this all the way down to what is actually known. A volcano that killed 29,000 people in under 2 minutes has been in unrest for 7 years without erupting. That unrest surged in 2020 and 2021, faded so thoroughly that by 2024 it was releasing less seismic energy than before it started, and then produced the biggest swarm in the observatory's history in the autumn of 2025, with thousands of earthquakes a month and every other instrument on the mountain reading flat. Nothing came of any of it. The scientists who documented the first 5 years published a study saying, in effect, we do not know if this is over or paused. Then this year, 3 things changed at once. Since May, the summit has been swelling at rates roughly an order of magnitude larger, per month, than the anomaly those scientists called significant and important. Since late July, the earthquake count has nearly tripled and is running about 20 times the pre-unrest baseline, while still sitting at roughly 1/9 of what it was last September, and in each of the last 2 published weeks, exactly 1 earthquake has arrived from the corridor between the hydrothermal system and the magma storage, and the second one was a kilometre deeper than the first, alongside the return of hybrid events and a long-period event at the base of the crust. Against that, everything visible says nothing is wrong. Nothing has been felt. No event has exceeded magnitude 1. There are no fumaroles, and there have not been since 1970. The thermal springs have not warmed in 17 years. There is no thermal anomaly anywhere on the mountain. The gas pulse peaked 4 years ago and declined. The inflation rate is decelerating. The alert level is yellow, and the observatory says the short-term probability of eruption remains low. Both of those paragraphs are true. That is the whole situation. So let me be as useful as I can and tell you exactly what would need to happen for this to become serious, in order, so you have a checklist rather than a feeling. First, the deep event recurring, not the count. The count is the wrong number, and it has been the wrong number all night. What matters is whether that one anomalous earthquake from the corridor keeps arriving week after week, and whether it keeps trending downward. 2 in a row is a coincidence with a suggestive shape. 4 or 5 in a row, progressively deeper, is a trend. And a trend in that depth range is the connectivity the researchers said is required before an eruption. Second, hybrids and long-period events becoming routine instead of exceptional. 17 long-period events in 5 years is exceptional. 1 a week would not be. Third, the deformation reversing. Right now the 2 signals contradict each other, and that contradiction is genuinely reassuring, because it means no single coherent process is driving everything. If the inflation rate stops declining and turns back upward, while the seismicity stays high, the contradiction resolves, and the 2 instruments start telling the same story. That is the moment the situation changes character. Fourth, anything at all appearing at the surface, a new fumarole, a thermal anomaly on an overflight, a thermal spring finally breaking that 36.8-degree ceiling that has held since 2009. Any of those would mean the sealed lid on the hydrothermal system had been breached, and that would be visible from a helicopter rather than only from a seismometer. Fifth, and last, a phreatic explosion. A steam blast at the summit, throwing out old rock and ash and no fresh magma. That would be the expected next stage of an escalating sequence, and it is what happened on the 23rd of April 1902. And even then, hold the line, because this volcano has done it twice without consequence. There were phreatic eruptions here in 1792, and again in 1851 and 1852, and neither was followed by a magmatic eruption. The relationship runs one way only. Every magmatic eruption at Mount Pelée has been preceded by a steam explosion, but not every steam explosion has been followed by a magmatic eruption. Necessary, not sufficient. None of those 5 things has happened. Not one. As of tonight, every item on that list remains unticked, and the honest summary of Mount Pelée on the 11th of August 2026 is that it is a restless volcano at a yellow alert level, with a slightly unusual pattern in its seismic catalogue. There is a question I have been asked every time one of these stories comes up, and it deserves a direct answer rather than a hedge. Should anyone change anything? If you live in northern Martinique, nothing has changed, and the people whose job it is to tell you otherwise have not told you otherwise. What has changed is that the 12 commune pairing in the Orsec plan is worth knowing rather than assuming, and that the drill in January found a real problem with the roads, which is the kind of thing worth having an opinion about before it matters rather than during. If you're planning to travel there, go. The alert level is yellow, the summit is open to hikers under normal conditions, and the probability of an eruption during any given week remains, in the observatory's own words, low. If you are neither of those things, and you're simply someone who finds this fascinating, the useful thing you can do is remember what the actual watch criterion is, because when this story spreads, and it will, it is going to spread as a number. 331 earthquakes, 372 earthquakes. The count will be the headline, because the count is large and easy. The count is the wrong number. It has been the wrong number since the first sentence tonight. 228 of those earthquakes were the water system doing what it has done every week for 7 years. The number that matters is 1. I keep coming back to how small all of this is. That is what has stayed with me while putting this together. The entire story is built out of measurements that are almost nothing. A mountain moving half an inch a month. Earthquakes below magnitude 1 that nobody has felt. A single event at the base of the crust that released less energy than lifting a bag of shopping. Carbon dioxide seeping out of soil so quietly that the only way anyone noticed was that the trees stopped having leaves. Nothing in this story is visible, nothing in it is loud, and it sits on top of an event that killed a city in under 2 minutes on a Thursday morning while people were walking to work, having been told the week before that they were safe. That is the real shape of this hazard. Not that the mountain roars before it kills, that it barely whispers, and that we have built an entire apparatus of instruments and satellites and weekly one-page bulletins for the sole purpose of hearing something that quiet in time to get out of the way. So we watch, and what we are watching for is not a plume, not a tremor, not a headline. It is one line in one bulletin due around the 14th of August in a report written in a town this mountain has already destroyed once. And the only thing that matters in it is whether, for the 3rd week running, there is a sentence that begins with the word however.